There is something deeply unsettling about Mercury. Mercury is shrinking. Its crust is deforming, and evidence now suggests parts of its surface have moved within the last few 100 million years, far too recently for a planet this small. That alone breaks our models. Because Mercury also has an iron core that is far larger than it should be, a magnetic field that should have collapsed long ago, and a composition that doesn't make sense for where it orbits. The more precisely NASA measures Mercury, the less it behaves like a planet that evolved normally. Today, we're going to look at why Mercury is making NASA deeply uneasy. For billions of years, Mercury has been shrinking. This is not a theory, it is an observed fact. The planet's interior is cooling, and as it cools, the rock and metal contract. This causes the surface to wrinkle and crack, forming massive cliffs called lobate scarps that snake across the landscape for hundreds of miles. These scarps were first discovered in the mid-1970s by NASA's Mariner 10 spacecraft during its flybys of Mercury. They are the result of thrust faults, where one section of the planet's crust is pushed up and over the adjacent terrain. Think of it like the wrinkles that form on an apple as it dries out. Except Mercury is not drying out, it is cooling down. From these observations, scientists calculated that Mercury has shrunk in radius by about 7 kilometers. That might not sound like much, but for a planet with a radius of just 2,440 kilometers, it is significant. For a long time, the assumption was that this shrinking process happened early in Mercury's history and then stopped. The scarps cut through some older craters, but younger craters are superimposed on top of the scarps. So the scarps must be older than those craters. Based on crater density counts, the consensus view was that Mercury's scarps are mostly about 3 billion years old. But recent evidence suggests something very different. In 2024, a team of researchers in the UK made a surprising discovery. Using high-resolution images from MESSENGER's low-altitude orbital phase, they identified small fractures on top of some of the large lobate scarps. These fractures are called grabens, narrow linear troughs that form when the crust is stretched. Stretching might seem strange on a planet where the overall crust is being compressed, but the team realized that these grabens would occur if a thrust slice of crust was bent as it was pushed over the adjacent terrain. If you try to bend a piece of toast, it cracks in a similar way. The grabens are less than 1 kilometer wide and less than about 100 meters deep. These are very small features, and that is important, because in the harsh environment of Mercury, small features do not last long. The surface is constantly bombarded by meteoroids and comets. This process, called impact gardening, gradually erases small-scale structures by tossing material across the surface and filling in depressions. Based on the rate of blurring caused by impact gardening, the researchers calculated that the majority of these grabens are less than 300 million years old. That is geologically recent. It means that the scarps beneath them have been moving within the past few 100 million years, and if they were moving that recently, they might still be moving today. The team found 48 large lobate scarps that definitely have small grabens. Another 244 scarps were topped by probable grabens, which are not seen clearly enough in the available images to be certain. These structures are distributed across Mercury's surface, from 72 degrees north latitude to 76 degrees south. This is the first widespread evidence of geologically recent tectonic activity on Mercury, and it means that Earth is not the only tectonically active planet in the solar system. The discovery of recent tectonic activity tells us something important about Mercury's interior. It suggests that the planet's core is still cooling, and that cooling is happening much more slowly than scientists expected. Mercury's core is thought to be layered. At the center is a solid inner core, likely made of iron and nickel. Surrounding that is a liquid outer core, which generates the planet's weak magnetic field through a dynamo effect. Above that is a solid outer core layer, and finally a thin silicate mantle and crust. The fact that Mercury still has a global magnetic field is remarkable. The planet is tiny. Its rotation period is nearly 59 Earth days, which is very slow. Under normal circumstances, a planet this small and slow spinning should not be able to sustain a dynamo. Yet Mercury's magnetic field has existed for billions of years, as confirmed by MESSENGER. The continued activity of the magnetic field and the ongoing tectonic deformation both point to the same conclusion. Mercury's interior is still hot, the outer core is still liquid, and the planet is still losing heat, albeit very slowly. But why is the cooling happening so slowly? One possibility is that Mercury has a thick layer of insulating material. Some models suggest the planet is covered by a megaregolith, a thick blanket of broken rock and dust created by billions of years of impacts. This layer would slow the escape of heat from the interior. Another possibility involves the composition of the core itself. Some researchers think there is a layer of iron sulfide surrounding a silicon-bearing inner core. This sulfide layer would have a lower melting point than pure iron, allowing it to remain liquid longer. A third factor could be inefficient mantle convection, or even the complete cessation of it. If the mantle is not circulating heat effectively, the interior would cool much more slowly. All of these factors together could explain why Mercury is still shrinking today, billions of years after its formation. Now we need to talk about Mercury's orbit, because there is a chance, however small, that the planet will not stay where it is. Mercury's orbit is already the most eccentric of all the planets in the solar system. Its distance from the Sun varies from 46 million kilometers at perihelion to nearly 70 million kilometers at aphelion. The orbit is also inclined by 7 degrees relative to the plane of the ecliptic, the disk in which most of the planets orbit. For a long time, astronomers assumed that the orbits of the planets were stable. Isaac Newton's laws of motion and gravity predicted that the planets would continue in their elliptical paths around the Sun indefinitely. And for most practical purposes, that is true. But in the late 19th century, the French mathematician Henri Poincaré showed that even in a simple system with just 3 bodies, such as the Sun and 2 planets, it is impossible to calculate exact solutions to the equations of motion. Small changes in initial conditions can lead to very different outcomes over long timescales. This is what we now call chaos. The solar system is chaotic. The planets interact with each other through gravity, and those interactions accumulate over millions of years. The positions of the planets become impossible to predict with certainty beyond a few tens of millions of years into the future. In 2009, Jacques Lascar and Michael Gastineau at the Paris Observatory published a groundbreaking study. They ran 2,501 numerical simulations of the solar system, each with slightly different starting conditions. Mercury's initial position varied by about 1 meter between simulations. The results were disturbing. In most simulations, everything proceeded normally. But in about 1% of the cases, Mercury's orbit became unstable. Its eccentricity increased to the point where the planet's path crossed the orbit of Venus. Once that happens, Mercury is in serious trouble. A close encounter with Venus could send Mercury crashing into the Sun, eject it from the solar system entirely, or send it on a collision course with another planet. In some of the simulations, Mercury collided with Venus. In others, Mars was destabilized and ejected from the solar system. In a small number of cases, Mercury or Mars collided with Earth. Let's be clear about what this means. If Mercury were to hit Earth, it would not be an extinction event. It would be a planet-ending event. Nothing would survive. The entire crust would be vaporized. The oceans would boil away. The atmosphere would be stripped off. By comparison, the asteroid that killed the dinosaurs 65 million years ago was only 6 miles across. Mercury is 3,032 miles in diameter. Now, the good news. The chance of this happening is roughly 1%, and even if it does happen, it would not occur for at least 3 billion years. So there is no immediate danger. But the fact that it is possible at all is unsettling. Mercury's orbit is not as stable as we once thought, and the reason comes down to a subtle interaction between Mercury and Jupiter. Mercury's perihelion, the point where it gets closest to the Sun, precesses. That means the orientation of its elliptical orbit slowly rotates over time, like the hand of a clock. This precession occurs at a rate of about 1.5 degrees every 1,000 years. Most of this precession is caused by gravitational interactions with the other planets, particularly Venus, Earth, and Jupiter. But about 7.5% of Mercury's precession is due to the effects of general relativity. The curvature of spacetime near the Sun causes Mercury's orbit to rotate slightly faster than Newtonian mechanics would predict. This was one of the first confirmations of Albert Einstein's theory of general relativity. In the early 20th century, astronomers had noticed that Mercury's orbit was not behaving exactly as Newton's laws predicted. Einstein's equations provided the missing piece. But general relativity also plays a role in the long-term stability of Mercury's orbit. It turns out that without the effects of general relativity, Mercury would be 60 times more likely to become unstable. Here is how it works. Jupiter's perihelion also precesses, but at a slightly slower rate than Mercury's. If the two rates were to fall into sync, a 1-to-1 resonance, Jupiter's gravitational tugs on Mercury would accumulate over time. This could pull Mercury off course. General relativity speeds up Mercury's precession just enough to keep it out of sync with Jupiter. But over billions of years, chaotic perturbations from the other planets can nudge Mercury's orbit closer to the resonance. If that happens, the instability unfolds. The simulations by Lascar and Gastineau show that if Mercury's eccentricity increases enough, it can cross Venus's orbit. From there, the gravitational interactions become unpredictable. In some cases, Mercury crashes into Venus. In others, the disruption spreads to Mars and Earth. It is worth noting that these simulations extend billions of years into the future, long after the Sun will have evolved into a red giant. By that time, Mercury will almost certainly be destroyed anyway, either swallowed by the expanding Sun or vaporized by its heat. But the fact remains. Mercury's orbit is not as stable as the orbits of the other planets. It exists on a razor's edge, held in place by a delicate balance of gravitational forces and relativistic effects. Right now, a spacecraft is on its way to Mercury. It is called Bepi-Colombo, a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency. It was launched in October of 2018 and will enter orbit around Mercury in late 2026. Bepi-Colombo is actually two spacecraft joined together. One is the Mercury Planetary Orbiter, built by Europe. The other is the Mercury Magnetospheric Orbiter, called MEO, built by Japan. Once they arrive, the two will separate and enter different polar orbits around the planet. The mission has already made 6 flybys of Mercury, using the planet's gravity to slow down and adjust its trajectory. The most recent flyby occurred on January 8, 2025. During these flybys, the spacecraft has been testing its instruments and taking measurements of Mercury's surface and environment. One of the key goals of Bepi-Colombo is to understand Mercury's formation. The spacecraft will map the composition of the surface in unprecedented detail, looking for clues about the planet's origins. It will also study the structure of the core using gravity measurements and laser altimetry. If Mercury really did form from a giant impact, the surface should show evidence of a temporarily molten mantle, a vast magma ocean that solidified in a specific way. Bepi-Colombo will look for that evidence. The mission will also search for more grabens, those small fractures on top of the lobate scarps that indicate recent tectonic activity. The images taken by Messenger had limited resolution, especially in the southern hemisphere. Bepi-Colombo's cameras will provide much more detailed coverage, potentially revealing hundreds of additional grabens. Another important measurement will be the detection of Mercury's deformation in response to the Sun's gravity. As Mercury orbits, the Sun's tidal forces cause the planet to bulge slightly. By measuring how much the planet deforms, scientists can learn about the interior structure and the thickness of the crust and mantle. Bepi Colombo will also investigate Mercury's magnetic field and the processes that generate it. The spacecraft will fly through regions of the magnetosphere that have never been sampled before, including the polar cusps, where solar wind particles funnel down toward the surface. And there is one more mystery that Bepi Colombo might help solve: the mystery of Mercury's volatiles. Here is something that does not make sense. Mercury should not have volatile elements on its surface, but it does. Volatile elements are substances that evaporate at relatively low temperatures. These include potassium, sodium, sulfur, and even water ice. On a planet as close to the Sun as Mercury, with surface temperatures reaching 430 degrees Celsius, these substances should have been boiled away long ago. Yet MESSENGER detected significant amounts of potassium and sulfur on Mercury's surface. It also found water ice in permanently shadowed craters near the poles. These craters never receive direct sunlight, so the temperatures inside them remain below -170 degrees Celsius. The ice is trapped there, preserved in the cold and dark. This is deeply puzzling. If Mercury formed where it is now, so close to the Sun, it should have lost its volatiles early in its history. If it formed farther out and was later moved inward by a giant impact, the impact itself should have vaporized these elements. So where did they come from? One possibility is that the volatiles were delivered after the giant impact. Comets and asteroids bombarding the planet could have brought water and other volatile compounds. Over billions of years, enough material could have accumulated to explain what we see today. Another possibility is that Mercury accreted interplanetary dust very slowly over vast timescales. This dust would contain trace amounts of volatiles, which could have gradually replenished the surface. But there is a third possibility. What if the giant impact theory is wrong? What if Mercury's high iron content and the presence of volatiles both have a different explanation? Some researchers have proposed that Mercury formed from a grazing collision between two bodies of similar mass. In this scenario, the impact would strip away about 60% of the mantle, but would not generate as much heat as a head-on collision. This could allow some volatiles to survive. Recent simulations by Patrick Franco and colleagues at the National Observatory in Brazil support this idea. They showed that a grazing impact between two protoplanets of similar size could produce a remnant with a mass and core-to-silicate ratio that matches Mercury's current values. The collision would need to occur at relatively low velocities, between 2.5 and 3.5 times the mutual escape velocity. This scenario is statistically more plausible than the traditional giant impact theory. Grazing collisions between similarly sized bodies are much more common than catastrophic head-on impacts. If this is correct, then much of the debris from the collision would have been ejected into space, carried away by the gravitational pull of other developing planets like Venus and Earth. Some of it might even have been incorporated into Venus during its formation. Bepi Colombo will test this theory by analyzing the surface composition in detail. If the grazing impact model is correct, the distribution of elements on Mercury's surface should match the predictions of the simulations. So what happens next? In the short term, Bepi Colombo will arrive at Mercury and begin its mission. Over the course of 1 year, with a possible 1-year extension, the spacecraft will gather data that could finally answer some of the biggest questions about this enigmatic world. But in the long term, Mercury's future is uncertain. If the predictions are correct, there is a small chance that Mercury's orbit will destabilize over the next few billion years. The planet could collide with Venus, crash into the Sun, or be ejected from the solar system entirely. In the worst-case scenario, it could even collide with Earth. But even if Mercury's orbit remains stable, the planet will not last forever. In about 7 to 8 billion years, the Sun will exhaust its hydrogen fuel and begin to expand into a red giant. Mercury will almost certainly be destroyed at that point, either swallowed by the expanding star or vaporized by its heat. Until then, Mercury will continue to shrink. Its interior will continue to cool. the lobate scarps will continue to grow, driven by thrust faults deep beneath the surface. And every few million years, a new graben will crack open on the crest of a scarp, a tiny fracture that marks the latest movement of a fault that has been active for billions of years. Mercury is a planet that should not exist. It is too metal-rich. It is too active. It is in the wrong place. And yet it is there, circling the sun every 88 days, a small, dense world that holds secrets we are only beginning to understand. Let's step back and consider what we have learned. Mercury is not a dead world. It is geologically active. It has a magnetic field. It is still shrinking. And it is doing all of this in a way that defies many of our expectations. The discovery of recent tectonic activity tells us that Mercury's interior is still cooling, billions of years after the planet formed. This has important implications for our understanding of planetary evolution. It suggests that small, rocky planets can remain active for far longer than we thought, especially if they have thick, insulating layers or unusual core compositions. The instability of Mercury's orbit reminds us that the solar system is not as stable as it appears. Over long timescales, the gravitational interactions between planets can accumulate in unpredictable ways. Mercury exists in a delicate equilibrium, and that equilibrium might not last forever. The mystery of Mercury's formation is still unsolved. We do not know if it was struck by a giant impactor, formed from iron-rich material, or resulted from a grazing collision between two similar-sized bodies. Each theory has strengths and weaknesses. Bepi Colombo might provide the evidence we need to decide between them. And the presence of volatiles on Mercury's surface challenges our assumptions about planet formation. It shows that even in the harshest environments, volatile elements can survive and accumulate. This has implications not just for Mercury, but for exoplanets orbiting close to their stars in other solar systems. Mercury is not just important for understanding our own solar system. It is important for understanding planets everywhere. Astronomers have discovered thousands of exoplanets in recent years. Many of them orbit much closer to their stars than Mercury does to the Sunday. These worlds, known as hot Jupiters and super-Earths, experience extreme temperatures and intense radiation. Some of these exoplanets are thought to be similar to Mercury. They are small, dense, and iron-rich. They are sometimes called super-Mercuries. Observations suggest that these kinds of planets might be quite common in our galaxy, accounting for perhaps 10 to 20% of all planets. If Mercury formed from a grazing collision, then super-Mercuries might have formed the same way. If Mercury's volatiles were delivered by comets, then the same process could be happening on exoplanets. If Mercury's core is still cooling because of a thick insulating layer, then other small planets might remain active for billions of years. Every piece of information we learn about Mercury helps us interpret the observations of distant worlds. It gives us a framework for understanding how planets form, evolve, and die. There is one more thing we need to talk about. The thing that makes Mercury truly strange. Mercury is shrinking. We know that. But we do not know how much it has shrunk in total. The 7-kilometer estimate is based on the size of the lobate scarps. But that assumes every scarp represents a single episode of movement. If the faults beneath the scarps have moved multiple times, then the total shrinkage could be much greater. And we do not know when the shrinking will stop. If Mercury's core is still cooling, then the shrinking will continue. But how long will that take? Another billion years? 10 billion years? We also do not know if Mercury is experiencing quakes. On the Moon, seismometers left behind by the Apollo missions detected moonquakes clustered near lobate scarps. The most detailed images of the Moon's surface from orbit show boulder tracks on the faces of scarps, presumably dislodged by recent quakes. If Mercury is still shrinking, then it should be experiencing Mercury quakes, but we have no way to measure them. Bepi Colombo is not carrying seismometers. Future missions might, but none are currently planned. And then there is the question of Mercury's ultimate fate. Will its orbit remain stable? Will it be destroyed by the Sun in 7 billion years? Or will it be flung into interstellar space long before that? A rogue planet drifting through the darkness between stars? We do not know, and that is both frustrating and exhilarating. Mercury is a planet that challenges everything we think we know. It is too dense, too active, and too strange to fit neatly into our models. It is shrinking, cooling, and possibly unstable. And it is doing all of this in a way that we are only beginning to understand. The more we study Mercury, the more we realize how much we do not know. Every answer brings another question. Every measurement reveals another anomaly. But that is how science works. We observe, we measure, we test our theories against the data, and when the data does not fit, we revise our theories. Bepi Colombo will provide new data. It will map the surface, measure the gravity, study the magnetic field, and search for evidence of recent tectonic activity. It will help us understand where Mercury came from and what is happening to it now. But even with all of that, Mercury will remain a mystery, because the more we learn, the more we realize how little we truly understand about the formation and evolution of planets. For now, all we can do is watch and wait and wonder what else this small, strange world has left to reveal.